Here's a mistake no physicist would ever make. Adding a force to an energy. And the reason it's forbidden isn't that the numbers come out wrong. It's deeper than that. It's the same reason you can't add 3 apples to 2 oranges and call it 5 of anything. They're different kinds of thing. So physics has a hidden grammar. A set of rules that every meaningful equation has to obey, not about whether it's true, but about whether it even makes sense. We call it dimensional homogeneity. And an equation that breaks it has no dimensional meaning at all, no matter how right the numbers look. Here's the trick that makes it all work. Every physical quantity is secretly a recipe of just 3 ingredients: mass, length, and time. Write them m, l, and t. A speed is a length divided by a time. An energy is a mass times a length squared over a time squared. Strip away the meaning, and what's left is the dimension. The rules are almost boringly simple. When you multiply 2 quantities, you multiply their dimensions. When you raise a quantity to a power, you raise its dimension to that same power. Nothing surprising yet. An area is length times length, so its dimension is L squared. The 2 L's just snap together. But here's the rule that really bites. A sum of 2 quantities only makes sense if both pieces have the exact same dimension. And then the sum has that dimension too. This right here is what forbids adding a force to an energy. It's the apples and oranges rule, written in symbols. Rule 4 is a quiet one. Plain numbers, constants, coefficients, anything you'd find on a ruler carry no dimension at all. A 2 is just a 2. It doesn't drag any mass or length along with it. So when you check an equation, you can ignore the bare numbers entirely. And rule 5 is where it gets interesting. Anything sitting inside a function like sine or exponential or logarithm, that argument has to be a pure number. Dimensionless. Because think about what the exponential really is. It's an infinite sum 1 plus x squared over 2, and on and on. Now look at that sum. You're adding x to x squared to x cubed. But the sum rule says you can only add things of the same dimension. And x squared can only match if x has no dimension at all. So the argument is forced to be a pure number. The rules feed into each other. And here's the beautiful part. Suppose you see the expression e to the wt equals 1, where t is a time. You don't know what w is, but the exponent, w times t, must be dimensionless. So w has to cancel the time, which means w has dimension 1 over time, a frequency. The equation just told you the units of something you'd never met. Let's put it to work on a formula you actually know. A body thrown upward. Its height is the starting speed times time, plus 1/2 times g times time squared. 3 pieces. For the equation to make sense, every single piece has to come out as a length. Left side height, that's a length L. First term. A speed is length over time times a time. The times cancel, leaving a length. Good. Second term, the 1/2 we ignore. G is an acceleration, length over time squared, times time squared. Again the times cancel, a length. All 3 pieces are lengths. The equation is homogeneous. Now, if you want to do this systematically, for many quantities at once, you just stack all those exponents into a table. 1 column per quantity, 1 row per ingredient, mass, length, time. That table is called the dimensional matrix. It doesn't fall out of the sky. It's literally just your list of dimensions, copied down. For a velocity, the column reads 0, 1, -1. And here's the quiet magic. Asking which combinations are dimensionless becomes asking which exponent vectors solve m times a equals 0. A homogeneous linear system. The whole question of dimensions has turned into linear algebra, and that's exactly the machinery the Buckingham pi theorem runs on. So that's dimensional homogeneity. It starts as a rule against nonsense, you can't add apples to oranges, and it ends as a tool that tells you the dimension of things you've never seen and turns physics into algebra. A good equation respects it. And when it does, it means the same thing in every system of units. Sometimes the grammar is the whole story.